Our next speaker, Kyle Young, is rather different to Steve. Instead of spending 35 years in one place, he's moved about quite a bit. PhD and postdoc work in Canada, a lot of work in Europe, Africa and South America, 4 years with the Environment Agency, and now for the last matter of months only, I think, University of Aberystwyth. And Kyle is going to talk to us about the stocking and catches in England and Wales. Thank you very much.
Am I mic'd? Oh, I am mic'd up. First of all, thank you very much to IBIS and AST for organizing what I think is a very timely conference. And thank you for giving me the opportunity to speak. I'm going to present data from a paper that was recently published exploring the relationship between stocking effort and angler rod catches in England and Wales. But I first want to thank various people. First are various colleagues, Ian Russell, Ian Dolben, who spent a lot of time managing some unpublished data that I was able to use. Particularly, I want to thank the thousands of anglers who, whether complete angler lies or not, filled out the form at the end of the season and sent it in. Because without those data, I couldn't have conducted this study. And finally, a disclaimer. Though these are Environment Agency and Natural Resource Wales data, and though I analyze them whilst an employee of both of those organizations, I have been asked and will make very clear I am speaking for me and not for those agencies. So don't go calling them tomorrow saying Kyle Young said this. Trust me, they won't listen anyway. But rest assured, these are my views. We have been stocking salmon a long time, quite literally since the time of Darwin. And it is, though this may be hard to believe, it is a mature debate. There is no debate that you can take a female into a hatchery and rear her offspring to a certain age, and by doing so, produce more adults than she would have done had she spawned in the wild. Not always, and not always by a lot. But if 5,000 eggs needs to produce 50 smolts, and we can give her 4,893, no matter how crap their survival is, and it will be crap, on average, we'll get more adults. Tons of data and no real debate. Nor is there a debate that doing that damages wild population productivity. It's almost a requirement. Lots of data, no real debate. The debate is where those demographic advantages and those population evolutionary ecological risks balance off, that it makes sense to intervene. That is the meaningful debate we need to be having. So I'm going to frame that debate, and then I'm going to show you some catch statistics from England and Wales. Lots of the data, particularly in the last 15 or 20 years, that we have to speak to both of those issues comes from really remarkable advances in molecular genetic techniques. This is my view of molecular genetics, and this was Darwin's view. He could have predicted 90% of the papers in the last 20 years without knowing anything about genetics. They're fairly logical, but these tools have given us remarkable insights to what's happening. But what it really comes down to is the phenotype. This is the fundamental unit of natural selection. The bird looking for moths isn't selecting alleles. It's selecting a moth that it can see. There are alleles, there are genes underlying those color differences. But when you change a habitat by throwing a bunch of soot in the air and change the color of the bark, natural selection favors a different phenotype. The same holds for streams and hatcheries. Here we have a white moth in a stream doing all the things that white moths do. Finding somewhere to dig a red, digging a red, choosing a mate. The males are fighting. It's timed emergence, it's rearing in the stream, territorial, drift feeding, la-di-da-di-da. All of these events imposing natural selection on survival, growth rate, et cetera, et cetera, et cetera. You take the white moth and stick it on the black tree, raceway ripening, egg stripping, random mating, pond rearing, schooling, search foraging, etc., etc., etc. All of those are changing the relationship between the phenotype and fitness. That is the definition of natural selection. What is the covariance between phenotype and fitness? The ultimate fitness is how many adults you produce, but there are components of fitness, growth rate, things like that. This cycle of taking white moths, putting them on a black tree, and sending them back into the white tree world has been best studied, for better or for worse, not with Atlantic salmon, but with steelhead trout from North America. And it ain't as bad as it sounds. Despite being a little bit smaller in maximum size and better looking and better fighters, they're essentially the same fish. 1 to 5 years in freshwater, longer as you go north. Mostly 1 to 5 years in saltwater, longer as you go north. Males maturing in the stream before going out. Okay? They are, for more or less, the same fish. In particular, this river in western Oregon, which flows into the Columbia, has provided us really the best insight into that cycle we were just looking at. This was any other river in the Northwest. It had a big hydropower weir. The fish were disappearing. And about 20-odd years ago, Oregon Fish and Wildlife decided that they would do a wild broodstock program to try and restore this run. And bless them, a few individuals at ODFW in Oregon State saw the technological writing on the wall, and every single adult that passed that weir had a scale sample, a fin clip, a length, and a weight. Fin clips just went into the freezer in Corvallis. They knew that in 10 years or so, it would be like buying a McDonald's hamburger. Send them to the lab, bing, get your data. And that's what they've done. And there have been some really quite remarkable papers that have come out of this data set, and they continue to churn through them. One of the first was this one. And I remind you, this is a wild broodstock program. And so what they were able to do is over these 20 years, they know the lifetime fitness of every individual fish. They know how many adults it produced. They know how many grandchildren it produced, and they know how many great-grandchildren it produced. And so they can ask, what is the relative reproductive fitness of taking a wild fish, taking it into the hatchery, having it produce offspring? What is the fitness of its offspring after one generation of captive rearing? The answer is about 85% of that of a wild fish. So after one generation, you've reduced its fitness in the wild by 15%. If you're unlucky enough to get a hatchery-reared fish and put it in the hatchery, its fitness will be about 30% of a wild-born fish. So what you see is a very rapid decline due to artificial selection and domestication selection. The shape of this curve is exactly what one would predict from selection acting on heritable phenotypic variation. Rapid change at the beginning, and once you're out here, it is truly just cormorant food you're throwing in the river. They will have almost no reproductive success when they return. A far more interesting paper just came out, and it is a simple yet very difficult figure, so we're going to go through it. And what they were able to do is they take a bunch of wild fish into the hatchery. They know the lifetime fitness of each of those fish. They then know the lifetime fitness of each of those offspring. And that's what this figure shows. On the x-axis, this is the number of adults produced by a wild broodstock bred in the hatchery. Okay? On the y-axis is the average number of adults produced by their offspring in the wild. So we'll do a couple of examples. This little missy comes into the hatchery, and she is astronomically successful and produces 55 adults. So that's the x-axis. Those 55 adults, on average, produce about 0.2 adults each. Okay? This unlucky lady, she came into the hatchery and produced about 2 adults. Those 2 adults produced, on average, 2.8 adults when they came back to the wild. Okay? So it's 2 generations. Each of these points is a lineage. There are a few things to note from this figure. First, stocking works. Look at these numbers. You have individual fish producing 20 adults, 30 adults, 40 adults, 50 adults. Okay? 2, there's severe mating skew. Most fish produce very few adults. Just like 10% of anglers catch 90% of the fish, 10% of the spawners produce 90% of the adults. And that's true in the wild, and it's true in the hatchery. Finally, note that there's a trade-off. Those phenotypes that do well in the hatchery, so out here on this x-axis, that lineage does very poorly when it's returned to the wild. Whatever we're selecting for in the hatchery does poorly in the wild that next generation. Notice they're all below 1. So you're producing tons and tons and tons of fish that are coming back and not replacing themselves in the wild. Year after year after year after year. It's like pumping narrow-beaked finches into a deep-beaked population, year after year after year. So what? Well, luckily, in Oregon, Washington, Idaho, every hatchery fish gets an adipose clip. And so you can go out to populations, and if there's a counting weir or if anglers are filling out their forms correctly, you can figure out what proportion of spawners are of hatchery origin. And you can do that, well, you can't, Mark Chilcote can, for 32 steelhead populations, 26 coho, and 36 chinook. And you can then ask, this is our stock recruitment curve, what is the slope at the origin? What is the productivity of that population? How many adults does an adult produce at low density? And this is the answer you get. And it's the catch-22 of stocking. On the x-axis is the proportion of hatchery spawners in the population. On the y-axis is the population productivity, the number of adults an adult produces across all of those populations. And what you can see, here are pure wild populations. Steelhead adult will produce 4, Chinook and coho, they're rats, so they produce about twice as many. If we had pink and chum, they'd be up there somewhere. So a wild steelhead population is producing about 4 adults per adult. If you double the population size, so half of the spawners are hatchery produced, you cut the productivity in half. So you're spinning your demographic wheels whilst eroding local adaptation in the population. The impact of hatchery fish from wild-type broodstock hatcheries was no less adverse than hatchery fish from traditional domesticated stocks. Thinking back to that other curve, that makes perfect sense. If you have a true hardcore hatchery population, well, they're not really interbreeding with the wild fish because they're so lame. So you just, half the fish don't reproduce. If you've got a wild broodstock population, they are interbreeding and constantly reducing fitness of your wild population. So this is what we're doing. Here's our river in 1324. Put some dams in, bunch of cows, a city, some concrete. This is what our stock recruitment curve looks like. And then we stock, and the stock recruitment curve gets pushed down again. So why do we do it? In England and Wales, because of angling. We can say mitigation, we can say restoration, we can say investigation. We want more fish to catch, is the bottom line. So, do we get more fish to catch? Finally, back to the topic, Atlantic salmon. So I have data from 62 rivers over 15 years. So there's stocking data and angler catch data. 42 of those rivers had at least one stocking event. So we have a natural experiment. Each of these rivers has the conservation limit, which you've seen, basically an estimate of its habitat size. How many adults should it produce? So we can ask this question. We control for the region, we control for the conservation limit. How many fish should it have? We control for the year, we control for net fisheries. And we ask, does mean rod catch go up with mean stocking effort? And does annual rod catch go up with annual stocking effort? No. Mean rod catch does not go up with mean stocking effort. These are the 62 populations. Over here are those with no stocking, and in black are those rivers with stocking. On the y-axis is the mean residual rod catch. There are a few things to notice. One, the black spots aren't way above and they aren't way below. The mean is the same. Stocked catchments and unstocked catchments have the same catch statistics. The other thing to notice is that the black dots don't trend up as mean stocking effort goes up. The more you stock, based on these data, you don't get more fish. It's basically a random shotgun blast. The final thing to notice is the river Tyne, which I've been asked to highlight. It is indeed above average. It is above what one would expect. It's not going to get Newcastle into the Champions League, but, it's doing all right. For the 42 stocked catchments only, we can ask, does annual stocking increase annual rod catch? And we do this with a simple correlation coefficient. Varies from -1 to 1. If it's negative, it's negative. If it's totally unrelated, it's 0. And if it's positive, it's positive. No. Annual stocking effort does not affect annual catch statistics. So this is the type of annual stocking effort. Let's just look at total. These are the 42 rivers. This is the distribution of correlation coefficients. This is 0. Some are positive, some are negative, and the mean correlation coefficient is 0. So if you were to randomly select a bunch of correlation coefficients, they might look like these. We can ask the bonus question. Do rivers for which annual stocking appears to increase annual catch have higher than average mean rod catches? Catch 22, take 2. The more successful a stocking program is, the more it damages the wild population. Those rivers for which the annual correlation appeared to be positive tend to have lower than expected mean rod catches. The answer to that blue arrow appears to be no. So the risks and the damage we're inflicting on these populations doesn't appear to be balanced by improved catches. Now, in some ways, that's the only good answer. If catches were going up, we could be absolutely sure we were damaging the population. If catches were dramatically going down, we could be pretty sure we were damaging the population. At least here we have the possibility of saying all the stockfish die the second they leave the hatchery, in which case we're largely innocent. And so the question then is, when do the benefits, and we know they are benefits, we know we can get more adults, is when do those balance out the damage we're doing? And what situation are we willing to risk the evolutionary and ecological integrity of a population to have more adults? And so instead of ending on a conclusion, I will end with that question. Thank you very much.
Thank you very much indeed, Kyle. I suspect there will be a lot of questions for that stimulating talk. We only have time for one at this stage, but again, we can return to it, of course, in the general discussion. Who would like that one? Yes, please.
Could I just clarify something? The younger the year stocking, when was that stocking taking place? Were you defining between younger the year that was stocked out as first feed fry as opposed to in the autumn?
So for each year has the catch statistic. And to get the stocking effort for that catch statistic, you go back 1 year and see how many smolts were stocked. I assumed everything came back as 2.1, which the vast majority of them do. So you go back 1 year for your smolt stocking effort, 2 years for your par stocking effort, 3 years for your young of the year
I suppose what I'm asking is, did you look at when those young of the year were put out, whether they were put out as very early fry or put out in the autumn as older fry?
They all got lumped, and the reason was, and Ian will know this well, for some rivers it says, for other rivers it doesn't. And so it just says fry. So I just said, everybody that says fry is a fry. Spring, summer, fall,